Hello there, I hope you're doing well. It's me, Monday Dennis Max Maths, back with O-level physics revision, and we're actually looking at the topic of waves. So my contacts are here. The email address is right here. If you want to write to me, please email me so I can assist you further to comprehend the physics subject. So this is the fifth part of the O-level waves. I've named it Waves Part 5. Please subscribe to my channel. I encourage you, please subscribe to my channel, and so that you get the notifications of the videos that I will be uploading later on. So this time we're looking at mechanical or material waves and electromagnetic waves. So we're going to look at the mechanical waves and electromagnetic waves. Then later we shall look at also progressive waves and the stationary waves. Now, mechanical waves are waves produced by vibration of a material medium. So the waves that result from vibration of a material medium, those waves are called mechanical waves. So mechanical waves need a material medium to travel. So they cannot travel through vacuum. They cannot travel through free space. Mechanical waves, I want you to remember this, that mechanical waves, by definition, they are waves produced by vibration of a material medium. And one of their properties is that they need a material medium to travel. So they can't travel through free space, or what we call a vacuum. Always write the right spelling of vacuum. Don't write V-A-C-C. It is V-A-C-U-U-M. Now, as a mechanical wave travels, it causes particles of that medium to vibrate. It causes the particles of the medium through which it will be traveling anyway to vibrate. And examples of mechanical waves include, we have water waves, sound waves. Now, sorry. You can't have water waves without water. Therefore, water waves will always need water. Sound waves will need a medium for them to travel. For example, sound can travel through air. It can travel through solids. It can travel through liquids. And we shall soon look at an experiment later, probably in the next video, or after the next video. We shall look at an experiment to show that sound requires a medium for its propagation. So earthquakes, waves on stretched strings, and many others. So these are mechanical waves. They require media for their propagation. So on the other hand, electromagnetic waves are waves that consist of perpendicular electric and magnetic field vibrations of high frequencies. So electromagnetic waves, by definition, this is the definition, they are waves that consist of perpendicular electric and magnetic field vibrations of high frequencies. So maybe just to make some little illustration here, if when we're talking about a mechanical wave, it means that we have two field vibrations of high frequencies. The first one will be a field which is an electric field. I've drawn it vertically. And then the second one, let me use blue, will be perpendicular. So this one was vertical. Then the other one will be, I'm trying to draw that it's horizontal, like this. So that I hope you will understand. It's quite funny here, but you have a field vibrating horizontally and one vibrating perpendicularly. Vertically. Those two are perpendicular. Now, so that two field vibrations of high frequencies, when one is an electric field and the other is a magnetic field, the two make up what you call an electromagnetic wave. So one more time, an electromagnetic wave is a wave which consists of perpendicular, electric, and magnetic field vibrations of high frequencies. In other words, you can say an electromagnetic wave is a wave which is made up of electric field vibrations and magnetic field vibrations of high frequencies vibrating perpendicular to each other or vibrating at right angles. The English I know you can find the words to use, but don't miss out the physics. So, as one of the properties, electromagnetic waves do not require a material medium to travel. That means they can travel through vacuum, or what we call free space. They can travel through free space. And examples of electromagnetic waves, these are quite many. You can look at gamma rays, X-rays, radio waves, and many others. But to understand the whole list, we shall look at what we call the electromagnetic spectrum, so that you look at all the examples of electromagnetic waves that you need to know. So one more time, what is an electromagnetic wave? An electromagnetic wave, we said, is a wave which consists of perpendicular, electric, and magnetic field vibrations of high frequencies. And the examples, we're going to look at all of them under the electromagnetic spectrum. So we are saying the electromagnetic spectrum. The electromagnetic spectrum, I'm abbreviating it as EM. The EM spectrum is an arrangement, or you can say is a band of electromagnetic waves in order of increasing wavelength or decreasing frequency. So we are looking at a band of electromagnetic waves which are arranged in order of increasing wavelength or decreasing frequency. Now look at this. If from left to right we are looking at decreasing frequency, and at the same time we are looking at increasing wavelength. Now one of the properties of electromagnetic waves, yes, I will list them later, but one of the properties is that electromagnetic waves travel at a speed of 3 exponent 8 meters per second. 3 exponent 8 meters per second. All of them, they have the same speed, in free space or in vacuum or even in air. That is 300 million meters per second. Let me write it. The pen is right here. So we are saying, instead I just removed the pen instead, that the speed of electromagnetic waves is 300 million meters in 1 second per second, or you can write it as 3 exponent 8 meters per second, like that. This looks weird. Okay, so now let's look at the electromagnetic spectrum. The electromagnetic spectrum with the electromagnetic waves that have the highest frequency and the shortest wavelength are called the gamma rays. So gamma rays start, followed by X-rays, followed by UV radiation, so you can say UV waves, followed by the visible light. Now the visible light here starts from red here. You remember the colors of the rainbow. Yes, you start with red. After red, what do we go to? And if you remember from your primary work, red, orange, yellow, green, indigo, and violet. Then we get ultraviolet. Okay, so after the visible light, we have infrared, we have the microwaves and the radar waves in the same class, and then we have the TV waves, and finally we have the radio waves. Now sorry, my throat isn't so good, that's why I keep doing those things. I hope you just understand. Okay, now The properties of electromagnetic waves that I want you to know include the following. Number one, all electromagnetic waves are transverse waves. They are all transverse. Number two, they travel through vacuum. They can travel through vacuum. They don't need a material medium for their propagation. And they travel at a speed of 3 exponent 8 meters per second. That is 300 million meters in 1 second. They possess energy, and they undergo reflection, they undergo refraction, they undergo diffraction, they undergo interference, and they can be polarized. They undergo polarization. Now I'm going to take you a little back. To the diagram, to the electromagnetic spectrum, this one here. I'm going to talk about each of these waves. The gamma rays, gamma rays are produced from radioactive materials. When the radioactive materials decay, they can emit gamma rays. I'm looking at the sources of these waves. X-rays are produced when fast moving electrons, what we call the cathode rays, are stopped by matter. When they are stopped by matter in an X-ray tube, you'll have fast moving electrons striking a tungsten target, and the energy they possess, the kinetic energy those fast moving electrons possess, will have some of it converted into X-rays, and the largest portion of it will be converted into heat. UV is produced by it can be produced even from the sun. The sun produces UV. Bulbs, yes, we have UV from bulbs. Visible light is produced it's produced by bulbs, by the sun. Actually, from these three here, UV, visible light, and infrared, these ones, they come, I can say their source is the sun, and even just bulbs, hot objects, yeah. But infrared, on a very specific note, infrared is produced, infrared radiations are produced by bodies whose temperature is above the absolute zero. Then we have microwaves. These can be produced by microwave ovens. Radar waves, you've heard of radars. Radar waves, and then TV waves, and then radio waves. Now the radar waves are used in aviation industries just to scan the sky and to monitor if there are any, if there are any, oh my god, English, if there so radar waves are used to find out if there are any incoming enemies, aeroplanes or jets that may cause danger. So they use radar waves. You can find out more. TV waves are produced by TV stations, and radio waves are produced by radio stations. Now, you have to know that gamma rays, X-rays, and UV, these ones here, they possess a lot of energy. And therefore there's something similar to them. They all cause photoelectric emission. Photoelectric emission means that if they fall on a metal surface, they can make that metal surface to emit electrons. That's what we call photoelectric emission. So when gamma rays, X-rays, or UV rays or UV radiations fall on a metal surface, they can cause photoelectric emission. And I said photoelectric emission is the process by which a metal surface releases electrons when irradiated with electromagnetic waves of high enough frequency. We shall look at the details in modern physics. Actually, I've already made a video of modern physics explaining that, and it's already available on my channel. A visible light is, the visible light, the one that enables us to see. So we are saying that their properties common to these three, so you have to know. And they also affect photographic plates. So because they carry a lot of energy. Now remember, the shorter the wavelength and the higher the frequency, the greater the penetrating power and the greater the energy the electromagnetic wave carries. Okay? So you have to know gamma rays, X-rays can damage body tissues, so you have to be very careful. UV radiations can cause sunburn, can cause blindness. Yes. And still these three, gamma rays, X-rays and UV rays, can cause fluorescence of some substances like zinc sulfide. They can make the zinc sulfide to give out the light because they have a lot of energy. Okay, that said, if you look at the visible light, I said comes from the sun, flames. It can come from lightning. It can come from sparks, electric sparks. It can come from lamps and many others. And its use, it enables us to see. It enables our eyes to see. It can, the visible light, depending on exactly which light is available, can make objects to appear in different colors. Okay, infrared here. Infrared radiations are produced by all bodies whose temperature is above the absolute zero. What is the absolute zero? That is a temperature above 0 Kelvin. And infrared causes a rise in temperature of a body. And this is a source of vitamin D, actually. Infrared, it helps in the synthesis of vitamin D, the infrared. And something very interesting about it that you have to know is that infrared is what you use in remote control. Please know that. It's the infrared that you use in remote control. And the infrared is used in remote control. It can also be used in night vision. And still, it can be used to produce, or you can say it can be used for heating effects. You can use it for heating or cooking, actually. Microwaves are basically used for heating also, though the infrared does it better. But microwaves can be used for specific heating purposes. For example, warming up food, you need a microwave oven, which will do without warming the whole oven. Radar waves, have talked about what they are used for. TV waves and the radio waves are used in TV and radio set broadcasts. Please, you have to know that. In the broadcasting TV, if they want to, for communication purposes, the TV waves and the radio waves are used. Now the TV waves, what does TV stand for? You know, TV stands for television. Yes. Phones use radio waves. You have to know that. Phones use radio waves. Let me get back a little to ultraviolet. Ultraviolet radiations or rays are used in photocells using photoelectric emission. They can be used, ultraviolet rays can still be used in detecting forgery of banknotes, forgery of academic documents, and forgery of other things. And they can also be used, UV rays can also be used to test good and bad eggs. Now I've tried to talk about each type of wave. Where you get challenges, please you can always consult or even research further. The properties, I've talked about them. Now note. The shorter the wavelength of an electromagnetic wave, the higher the penetrating power, and vice versa. I have already talked about this. We said that here the gamma rays have shorter wavelength and greater or higher frequency, and therefore they have the highest penetrating power. So thus gamma rays have the highest penetrating power and radio waves have the weakest penetrating power. Now let me look at the last comparative categories of waves, and those are the progressive waves and the stationary waves. Now a progressive wave is one which moves away from its source and spreads out continuously while transmitting energy. From the word progress, it means to move out, and you spread out continuously. So a progressive wave is one which moves away from its source and spreads out continuously while transmitting energy. Both transverse and longitudinal waves are progressive waves. I want you to know that both transverse and longitudinal waves are progressive waves. So if someone says, state examples of progressive waves, just pick any transverse wave or any longitudinal wave that you remember, and it's already a progressive wave. For example, here, examples of progressive waves include water waves, sound waves, waves on stretched strings, gamma rays, X-rays, ultraviolet, visible light, infrared, TV waves, radar waves, microwaves, radio waves, all those ones. On the other hand, a stationary wave is a wave which is formed when two progressive waves of equal amplitude, frequency, and wavelength. Now instead of saying frequency and wavelength, you can use speed, traveling in opposite directions, meet and combine. Meet and do what? And combine. So it doesn't mean that to repeat this definition, we are saying a stationary wave is a wave formed when two progressive waves of equal amplitude, equal frequency, and equal wavelength. So equal amplitude, frequency, and wavelength traveling in opposite directions meet and combine. Examples of a stationary wave or stationary waves. Let's look at the example of a stationary wave. I'm just going to illustrate here. When a wave travels from its source, so a wave comes from its source and strikes a barrier normally, it will be reflected along the same path. I want you to know that. And the incident wave together with the reflected wave form a stationary wave. Let me illustrate. So here we have two boundaries. We have this boundary and this boundary. So those are constrained boundaries. And then we send a wave from one point to another. So you see this wave has traveled that way. Now when it reaches here, because the boundary is fixed, that energy will be reflected back. And this is what will happen. You see that? Now the resulting pattern is what we call a stationary wave, because the energy that goes this way is brought back. You see that? So we end up with a stationary wave. Now, on the stationary wave, I want you to note this. We have these points here. Are you seeing those points there? Those ones. And then we have these points here. So the points, these points where the two waves are crossing each other, those ones, they are called nodes. And then these ones which were like hills or troughs, they are the antinodes. They are the antinodes. Okay. Now, this is a node. How many nodes do you see here? There is a node, 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 and a node. How many antinodes? How many nodes are here? 1, 2, 3, 4, 5, 6, 7, 8. How many antinodes? Having 1, 2, 3, 4 here, 5, 6, and 7. Please don't count also the other side. It's just one position like this. Someone was going to say there are 14. No. When you count here, it's 1, it means you have included even this upper part. 2, you have included even the other upper part. Just like that. Now, this is what we call the rest position. Supposing there was no wave, this is what we call the resting position or equilibrium position. So I want you to look at this. If you look at the white colored wave profile, the one we sent at first, you realize that from this point up to this point, for one complete cycle, that's one wavelength. Okay, that's lambda. And at the same time, from one crest to another, and this time I'm looking at the reflected wave, still we get lambda. So what do you realize? What about from one antinode to another? It's going to be lambda over 2. Do you see that? And from an antinode to a node, from an antinode to a node is lambda over 4, a quarter of lambda. Look at this is a quarter. Here we shall have a quarter. That's a half. 3 halves. And then the full whole number, 1. So terms used in stationary waves. The first one, we have nodes. A node is a point on a stationary wave which is permanently at rest. Or you can say a node is a point on a stationary wave which has 0 displacement from the equilibrium position. Number 2, so I will go back to the diagram. Now this node here is a point on a stationary wave, and this point is permanently at rest. Number 2, antinodes. Antinodes. You can just ignore this hyphen. It's just antinodes. So an antinode is a point on a stationary wave where particles are at maximum displacement from the equilibrium position. An antinode is a point on a stationary wave where particles are at maximum displacement from the equilibrium position. Taking you back, this is an antinode here because any particle here has maximum displacement from the equilibrium position. And antinodes or antinodes are also called the points of maximum displacement on a stationary wave. So note, the wavelength of a stationary wave is thus the distance covering 3 successive nodes or antinodes. I will go back still again, I won't get tired. You realize that this was a node here and a node here and a node here. How many are they now? There are 3 waves, 3 nodes, sorry, 3 nodes. Now nodes, we've already talked about this node. Conditions for a stationary wave to be formed: the 2 progressive waves combining must have equal amplitude. The 2 progressive waves combining must have equal frequency. The 2 progressive waves combining must be traveling in opposite directions in the same medium. Please, I want you to mark that. The conditions for a standing wave to be formed. Those are the conditions. Okay? Those are the what? The conditions. Examples of musical instruments which produce stationary waves: we have guitars, pianos, harps, flutes, and many others. Then characteristics of stationary waves. So number 1, there is no net transfer of energy in the medium. You have to know that. and the amplitude of vibration of the particles increases from 0 at the node to a maximum at the anti-node. All particles in 1/2 wavelength between two nodes are in phase, i.e. they are in the same direction at the same time. And then during each vibration, all particles pass simultaneously through their mean positions twice and with different maximum speed. This is a little confusing, but I just request you to read through. My time is up, so permit me to wind up here. By saying differences between progressive and stationary waves, please just copy them down and memorize them and understand now. Where you find challenges, please feel free to reach me. Okay, feel free to reach me where you find challenges, but I want you to read through this and you finish. Okay, I have just a quick question for you. Answer for me this question, please. You can also still pause and do this question. Okay, thank you for being nice students. May God bless you. Thank you for watching. Thank you for listening. Don't forget to subscribe and to remind your friends about this channel so that they can learn also like you are doing. Thank you very much. God bless you. Bye-bye.